Welcome back to another video of our course, Measure Theory for Probabilists. We now know something about L2 spaces, and that's what we're going to need today because we will be dealing with so-called densities, where a density of one measure with respect to a second measure is something you already know because, for example, you know something like these bell-shaped curves of the normal distribution, which is essentially a density of the normal distribution with respect to Lebesgue measure. Okay, let's get started. So let's get started with densities, and the result we're going to learn today is the Theorem of Radon-Nikodym, which I will show you on this slide here. But there are basically two new notations or notions. One is this here. That's called nu is absolutely continuous with respect to mu, or every mu zero set is also a nu zero set. And the other is nu has a density with respect to mu. And we didn't explain that yet. So let me, before I come to the result, come to these two notions. So first, nu has a density with respect to mu if this here holds. And let me remind you that this here could also be written like an integral. Let's say f of x dx over some a. But I have to be precise here, not just dx, mu dx. Like this here. So the measure nu on the set A can also be computed like this here. And that could look familiar. If you think about, for example, the normal distribution, then here mu would be the Lebesgue measure and the f would be the Gaussian function, the bell curve. And f is here density, and sometimes we write this here, f is d nu by d mu. And here you see why that is, because if you would write here d nu of x by d mu of x, then the d mu would cancel, and you have just d nu of x over a, which is then nu of a. So that's this way to write this, but I often on my slides use this here with this funny dot, f dot mu. So f is a function, mu is a measure. This here is the measure with density f with respect to mu. Okay, that's the one notion we need. The other one is absolute continuity. So if all mu zero sets are also nu zero sets, which means if every time I have a set A with mu of A 0, then also nu of A 0, then it's absolutely continuous. And we write it like this here. So if mu of A 0, then this is smaller, so it's also 0. Okay. If both hold, nu absolutely continuous with respect to mu, and mu absolutely continuous with respect to nu, then they're called equivalent. In contrast, we have something very different. And maybe I should draw a picture on the real line. So let's say this here. So this here would maybe be a density with respect to the Lebesgue measure of some nu. On the other hand, if I have another thing here with a density with respect to the Lebesgue measure, and that's the mu here, then I would find, let's say, the set A here, such that mu of A is 0, because this function here is flat on A. And on the complement of A here, the density of nu is flat. So that means So as I write here, mu and nu are singular because there's this one set A which divides nu and mu, so to speak. Well, and then we can go back and explain what the theorem by Radon-Nikodym is and what does it say. It's very powerful. It says having a density is the same as being absolutely continuous. And sometimes you can check absolute continuity, and then you already know, aha, there must be a density. Lebesgue's decomposition theorem, that's more general, and essentially Radon-Nikodym is only a corollary here. So in the general case, where I do not necessarily have that nu is absolutely continuous with respect to mu, I still have a mu, but it says I can decompose nu with two measures. One is absolutely continuous, and the other one is, as we said here, singular with respect to mu. So it's a decomposition. Nu is a sum, one absolutely continuous, the other singular to mu. Okay, let's try to say something about this. So first of all, having a measure, what does this mean? Having a density, what does this mean? First of all, densities are uniquely determined, almost surely. And second, there's a formula here. That's one kind of saying. How do you compute integrals with respect to measures which have a density with respect to a second measure? So this here is a measure with density, and this here is something easier because that's just an integral with respect to this one measure mu, and the f here you can just put in here into the bracket. That's what it says. So let's prove this. It's not too hard. First, uniqueness of the density. Okay, so I write down something rather stupid. Nu of A minus nu of A is 0, and A is the set G1 bigger than G2. Okay. Then uniqueness means both G1 and G2 are densities. Which means I can write nu of A as mu integral G1 over A. And minus nu of A, because G2 is also a density, I can write down this here. Then A is the set G1 bigger than G2. So on A, this here is positive. So this here is positive. So this here can only be 0 if mu of A equals 0. Otherwise, it's just not possible. And that means, mu of A is 0. That means G1 is less or equal than G2. Mu almost surely, but the same argument holds if I flip G1 and G2. So I find G1 equals G2, mu almost surely. Okay, that was the first thing. The second thing, so I prove here the two integrals are the same, and remember, integrals were constructed by first using simple functions or indicator functions, then simple functions, and then using approximations, all functions, all measurable functions. And I will argue here that it's enough to use very simple g's, so indicator functions, and then just say, well, it holds for indicator functions, then also for simple functions by linearity, and then using approximation for all functions. So for such a function, let me start with the left-hand side. F times mu, indicator A. Well, I measure A like this here. And what is this? By definition, that's the integral mu of f over the set A, or also mu f indicator A. And that means, yeah, here I'm on the right hand side if G is just the indicator. So this here holds. So this formula holds for indicator functions and by approximation then also for all functions. Okay, let's make 2 or 3 examples. First, we had this. So the Gaussian density you know here. Mu and sigma square are parameters. Lambda is one-dimensional Lebesgue measure. Then the measure with this density with respect to Lebesgue measure is the normal distribution. The exponential distribution is also a distribution with a measure, with a density with respect to Lebesgue measure. Here, for example, you want to compute the expectation, which is in terms of this lecture here. Well, I have the integral of the identity, because x here stands for the identity, of the exponential distribution, which is the distribution with density fx gamma with respect to lambda. And this formula tells me how to do this. I take the mu, which is the lambda here, and I integrate the product, x times gamma e to the minus gamma x. And I compute all this and I have 1 over gamma. You might know this. Then Poisson distribution, I can also say, well, it has a density with respect to the counting measure on n0. We have this, so mu is a sum delta k, k from 0 to infinity, and delta k of some set A is 1 if k is in A and 0 otherwise. Then I can say Poisson distribution is a distribution with a density, not with respect to the Lebesgue measure, but with respect to the counting measure. Okay, and now we are ready to prove theorem 4.16. We will need something here, what we had last time. Yeah, exactly, this one here. That's what we're going to need. Theorem of Ries-Fréchet. I have an L2 space and I have a continuous and linear map. And because it's linear, I can write the function as a scalar product for some h which is unique. Well, how does this apply here? So I have to have a continuous and linear map. And I will use the following. I have an L2 space. And here I will start having mu plus nu. That's also a measure. And I have this map here that goes to r, and f goes to nu integral with respect to f. So this is linear because the integral is linear. It's also continuous because if you have convergence of this here, so L2 convergence of this here, you also have convergence of the integral. Because only an L1 convergence is involved here, and I even have an L2 convergence here. That means by Ries-Fréchet, there's a function h such that this map here can be written as, well, I have the L2 space with respect to mu plus nu. So there's an h such that nu of f equals mu plus nu, and then this here is a scalar product f times h, so that's this here. That's what Ries-Fréchet gives me. And, well, you might now think that's already pretty much, because essentially what that says here is that h is the density of nu with respect to mu plus nu. Because if f here is an indicator function, then I have nu of a here, and I have here the defining property of nu having a density h with respect to mu plus nu. So I could write something here like nu is the same as h times mu plus nu. That's what the h here now stands for. But let me also mention that this here can be rearranged as follows by putting mu on one side of the equation and nu on the other side of the equation. And then I find nu integral f times 1 minus h equals mu integral over f times h. Now, okay, so h is something like the density of nu with respect to mu plus nu. And first of all, it's a density, so it's cannot be smaller than 0. I mean, Ries-Fréchet doesn't give me this, so I have to prove it that h cannot be negative. And h is also not able to be greater than 1, because h is the density of nu with respect to mu plus nu. And if it would be greater than 1, some measure of a positive thing must be negative here, which is not allowed. So, first of all, I claim that h is bigger than 0. So if I have nu and I measure h smaller than 0, that's of course bigger or equal than 0 because it's the measure of something. I can say, well, that must be the same as mu plus nu of h over the set h smaller than 0. Oops. And if I integrate a function on the set that it's negative, that must be smaller or equal than 0, which means all of this here is 0. So h is bigger or equal to 0, nu almost surely. And also, mu of h, I would set h bigger than 1. That's also bigger than 0, because I integrate a function over a set where the function is positive. Well, this here, by using this formula here, f is here the indicator that h is bigger than 1. That's the same as nu integral of 1 minus h over the set h bigger than 1. And that's smaller or equal than 0 because, well, on this set here, 1 minus h is smaller than 0. And that means here, yeah, all of this must be 0, which means, for example, h is smaller or equal to 1, mu almost surely. So that's one thing. Then something special. I mean, there is the pre-image of 1. So there's a set, and I call this here E. H is something like the density of nu with respect to mu plus nu. And if h is 1 here, then, okay, mu must be 0 on this occasion. So, because if h is 1, I have nu something equals mu something plus nu something. So the mu's here cancel, and the mu on the one hand, it cannot be negative because it's a measure. But on the other hand, it must be 0, otherwise this equation here just doesn't hold. So, let me say this here, and f equals the indicator of E. Then, as I said, mu of E must be 0. So why is that? On E, h equals 1, which means that's the same as mu of h over the set E. This here, by using once again this formula here, is the same as nu of integral 1 minus h over E. But on E, h equals 1, so this here must be 0. Okay, so mu is 0 on the set E here. Now I can define my decomposition already. I can write nu equals nu A for absolutely continuous plus nu S for singular with nu A of A equals nu of A but not E, and nu S of A equals nu of A intersect with E. And I have to show that this nu A and nu S fulfills the statements of the proposition. So nu A is absolutely continuous with respect to mu. That's what I have to choose. And nu S and mu are singular to each other. These are the two things I have to prove still. So if I want to show this, I choose a set A, which mu of A equals 0. Okay, then nu 1 minus h on the set A but not E. What's that? That I can rewrite as, well, that's the property we had here. I can write as mu of h on the set A but not E. But this here is 0 because choose A such that mu of A equals 0. So mu of A without E is also 0, and that must be 0 here. Then this here must also be 0. Yeah. Then I have h smaller than 1 on A without E, because if I'm not on E, so on E I'm h equals 1, but not on E I'm less than 1. And because of this here, I have nu A of, nu A of A, which is by definition nu of A without E, which is 0, because this here is 0, and I'm not on E here, which means this here is something positive, and the only way this here can be 0 is that nu of A without E equals 0, and that's what I use here. So I have nu A is absolutely continuous with respect to mu. That's what I just showed, because I started with a mu zero set and I ended up with proving that it's a nu A zero set. Okay, then we're almost there. Yeah, we have defined nu A and nu S. So nu A of A was nu of A without E, and nu S of A was nu of A intersection E, and H was something like the density of nu with respect to mu plus nu. And we said that this here is the defining property. So nu F equals mu plus nu F times H. So H is this density, and I now say I have a density G, which is H divided by 1 minus H, and that's now the density of nu A with respect to mu. But I can only do this if the denominator here is not 1. And where is it 1? On E. So indicator E complement. Then that's probably defined. And mu integral of G over some A, no matter what. G equals H divided by 1 minus H. and on E complement, which means I have to integrate over A minus E. I have, where is it? Here, mu, let me see, mu fh, some function f here, h, equals this new thingy here. And the function f is here indicator a without e divided by 1 minus h. I multiply by 1 minus h, and what stays is only nu of a without e, which is by definition nu a of a. So we have shown that G is the density of mu with respect to nu a. Yeah, and we are basically done. The only thing which is missing is uniqueness. But it's also not hard, and I think you can also read that in the manuscript. I mean, we already had the densities are almost truly unique, and here it's a bit more because we have the decomposition, but you can just use the uniqueness of the density of the new A's here. But let us come to Radon-Nikodym's theorem, where we had nu is absolutely continuous with respect to mu, and we have to find the density. So it has two things here. So from left to right. If nu has a density, then it's absolutely continuous. So having a density means that nu of A equals mu. Let's call the density Fa. And if I have a zero set here, then, well, the integral is also zero, so nu is also zero on this set, so absolute continuity holds. So from left to right, everything is clear. And from right to left, I can use the decomposition theorem. I can write nu equals nu A plus nu S. But the nu S here must be 0, because 0 is singular to nu also, and the decomposition here is almost truly unique. Yeah, so we have that nu equals nu A, and nu A by the decomposition theorem was absolutely continuous with respect to mu and had a density. And that's what we can use here in order to see that it has a density. So I can just say take density of nu A with respect to mu from theorem 4.16. And I'm done. Okay, so much for today. We are also done now with this chapter here on integrals. And next time we will start with the last chapter, which are product spaces. See you then.